After a detailed discussion of nuclear cell model, particularly the independent particle model of a nucleus, now we are going to discuss the predictions of the nuclear cell model. You will see in a successive series of lectures the different predictions of this nuclear cell model. So in this lecture, I am going to discuss uh, one of the important predictions of this nuclear cell model, and this is regarding the ground state spin and parity of the nuclei. Ground state spin and parity of the nuclei. When you say a spin of a nucleus, that means actually the total angular momentum of the nucleons present in the nucleus. So a spin of nucleus, means total angular momentum. So that at the in the place of term spin, you may also say total angular momentum. In fact, it has been seen that the nuclear cell model is very successful in predicting the ground state spin of a large number of nuclei. According to this model, the neutron and proton levels feel independently, and so we follow the following rules for finding the ground state angular momentum or spin and parity of the nucleus. So let us see what are the rules for finding the spin and parity of the ground state of different nucleus. You can see here. The first rule is for the even nucleus. When you say even nucleus, that means a nucleus in which the number of proton, that is Z, is even, and also the number of neutron is even. So if Z and N both are even, then such a nucleus is called even nucleus. And the rule says if you want to find the spin and parity of the even nucleus, then you have to find the total ground state angular momentum or the spin, and that will be actually equal to 0. If the nucleus is even, it means the number of proton is even, number of neutron is even, then the total ground state angular momentum or spin, which I have denoted by the symbol J pi or I. It means the spin is denoted by the symbol I or J pi, and that will be equal to 0. I have written here 0 plus as a superscript, which represents actually parity. And how this parity is found? Actually, for finding the parity, we use the following rule. If you write P for parity, the parity is determined by the number of neutron and number of proton of the last cell by this formula. This is actually defined as minus 1 raised to the power L into P plus L into N. It means this is actually the sum of the parities of the neutron and proton parities. So let us see here. By some example, we will clarify this rule. So remember, if the nucleus is even, definitely its ground state spin will be 0, because in even nucleus, all the cells are completely filled, so all the cells are closed, and hence the sum of the angular momenta of all nucleons is 0. And that's why we simply said that if the nucleus is even, that is the number of proton is even and number of neutron is also even, then all the cells will be closed, and since cells are closed, so the angular momenta gets sum up to give 0. For example, let us consider a nucleus of oxygen. This is 8O16. In 8O16, you can see Z is equal to 8, which is an even number, and N is also equal to 8, which is also an even number. So this is an example of even nucleus. Now we will write the nuclear configuration of this nucleus. You know, you have seen in the earlier lecture the energy level diagram, how the cells of the nuclei are filled by the nucleons. You have seen already. So the lowest energy level, for the lowest energy level, the subcell is 1s, and this configuration is written as 1s half 2p2n. It means what? It means half is actually the value of J, and 2p2n means 2 proton and 2 neutron. It means in this first cell there are 2 proton and 2 neutron. Okay. Now the second level is 1p3 by 2. Here the value of J is 3 by 2, and in this subcell the number of proton is 4 and number of neutron is also 4. Now the last cell in this nucleus will be 1p half. You know, p3 half, p3 by 2 is less in energy than p1 by 2, because the larger value of J means a smaller energy, you have seen. And in this last subcell, the number of proton is 2 and the number of neutron is also 2. So this is the nuclear configuration. Now you can see the last proton and last neutron of this nucleus is actually in this subcell 1p half. And so if you want to find the parity, what will be the parity? You can see this parity will be equal to -1 raised to the power L into P. L means, for P subcell, you know L is equal to 1, and P, this P is equal to 2. P means number of proton in the last subcell, and that is equal to 2. So we will write 2 plus, again L times N. L is 1 and N is 2. So this will be -1 raised to the power 4, and that will be equal to +1. So this nucleus will have even parity or positive parity. And since all the cells are closed, so as the rule says, in this case the ground state spin will be 0. So in fact we write this spin as I equal to 0 plus. Okay. Plus actually denotes the parity and 0 denotes the spin. Okay. Now take another example. The another important example is 14Si28. You can see in this nucleus Z is equal to 14 and N is also equal to 14, because Z plus N is 28. Okay. And what will be its nuclear configuration? This is 1s half 2p2n 1p3 by 2 4p4n. As you know, why 4? Because 3 by 2, it means J is equal to 3 by 2, and total number of nucleons is found by this formula 2J plus 1. So this will be 2 into 3 by 2 plus 1, and that will be equal to 4. So number of nucleons in this subcell 1p3 by 2 is 4 and 4. That is 4 proton and 4 neutron. Similarly, in 1p half, J is actually half. So what will be the number of neutron and proton? This will be 2 into half plus 1, and that will be equal to 2. So 2 proton and 2 neutron are in this subcell. And the last subcell is 1d 5 by 2, and in 5 by 2, as J is 5 by 2, so what will be the number of neutron and proton? That will be 2J. J is 5 by 2 and plus 1, and that will be equal to 6. So here there are 6 proton and 6 neutron in the last subcell. As all the subcells are completely filled, so the angular momentum get added to be 0, and so a spin or total angular momentum is 0. And again, if you will find the parity, you will find that this is actually even parity, that is positive parity. You can calculate it. P is equal to what? This is minus 1 raised to the power L times P plus N times L times N. L, again you can see the last subcell is D, and for D L is equal to 2. So 2 into 6 plus 2 into 6. So this will be minus 1 raised to the power 24, and that will be equal to plus 1. So its parity is even or positive. So a spin of this nucleus will be 0 plus. Okay, plus again represents the parity of the nucleus. You can take other examples like 2He4, which is even nucleus, again 38 Sr88, 76 Os 192, and 92 uranium 238. All these are even nuclei, and all these nuclei will have the spin or the total angular momentum or the ground state spin equal to 0, and all will have even parity. Okay, so I hope you have understand. This is a very simple rule. If you find that the given nucleus is even, you should write the total ground state angular momentum or the spin of the nucleus 0, and parity will be definitely positive. Okay, in fact this type of question is frequently asked in the examination like NET and JRF, so you should take care of it and remember this rule. Now the second rule says, for all nuclei with odd Z and odd N, the nucleons pair off as possible, and so the spin is due to the single unpaired nucleon. Okay, you have understand or not? In fact, if the nucleus has either Z number odd or the N number odd, in that condition there will be a pairing of the nucleons, and there will be some nucleon which will remain unpaired. That unpaired nucleon will determine the spin and parity of the nucleus. The nucleon which will get paired, their total angular momentum will be 0, but the nucleon which will remain unpaired, that will determine actually the parity and the spin. So you can illustrate it by some example, and after these examples the rule will be clear to you. You can see it here. I have taken here the first example of the nucleus 6C13. You can see 6 in 6C13, Z is 6, which is an even number. It means in this nucleus Z is even, but N will be 7, because 6 plus 7, that will be 13. So this is actually odd. This is odd. So you can say that this nucleus is even odd nucleus, and at the same time the nucleus may be odd even. Odd even. When you say even odd nucleus, it means Z is even and N is odd, And when you say odd even nucleus, that means number of proton is odd and number of neutron is even. Now let us write the nuclear configuration of this nucleus. You can see this is 1s half 2p12. Half means j, and you know the number of nucleon is found by this formula 2j plus 1. So this will be 2 into half plus 1, and that will be equal to 2. So in this first subcell, actually 2 protons and 2 neutrons are lying. Okay. Then 1p 3 by 2. Since j is 3 by 2, so the number of nucleons, each nucleon will be 4. So this is 4p 4n, and 1p half. So this subcell can accommodate 2 nucleons, 2 protons and 2 neutrons. But you can see here that there are since 6 proton, and you can see in the first subcell there is 2 proton, and in second subcell there is 4 proton. So total 6 protons have been distributed. And now the number of neutron in first subcell is 2 and in second subcell is 4. So only 1 neutron remains which is not lying in this second subcell. So in the last subcell there will be only 1 neutron. This is unpaired. This is the unpaired neutron. So in this case, the total ground state angular momentum or the spin and the parity will be determined only by this last neutron, because the angular momenta for the nucleons present in the filled subcells will be 0. So this last neutron, which is only 1, that will determine the parity and the angular momentum. So let us find it. First of all, I am finding what will be the parity of this nucleus. So use the formula P equal to minus 1 raised to the power Lp plus Ln. You can see the number of proton in the last subcell which will determine the parity is 0. And P, for P we will write 1. So 1 into 0 and plus again L times N. L is 1 and number of neutron present in the last subcell which determines the parity is equal to 1. So this will be equal to minus 1 to the power 1, which is minus 1. It means this nucleus will have odd parity, or you can say negative parity. Okay. And what will be actually the spin in this case? You can see spin means when you find the spin, you have to sum up the J value of the last of the nucleons present in the last subcell. Since there is only 1 nucleon in the last subcell, and for that J is equal to half. So the ground state spin, which we have denoted by the symbol J pi or I, that will be simply equal to 1 by 2. This is actually the value of J, you can see. And since the parity is odd, that is minus 1, so I have written here 1 by 2 and minus 1 as a superscript. Okay. Now see, another example you can see here, this is 6C11. In this case, Z is equal to 6 and N will be equal to 5, because 6 plus 5 will be 11. Now write the nuclear configuration. This will be 1s half. Since J is half, so number of proton and neutron in first subcell will be equal to 2 and 2. So this I have written here 2p2n. And then 1p 3 by 2. 1p 3 by 2. since J is 3 by 2, so number of proton will be 2J plus 1, that is 4. And number of neutron in this subcell may be 4, but since our nucleus has only 5 neutron and already 2 neutron has been accommodated in first subcell, so only 3 neutrons remains here. So in this case, actually the last subcell contain only 3 neutrons. In this case, you can see the value of J in the last subcell is equal to 3 by 2. So the ground state spin I or J pi will be equal to 3 by 2. And again, if you will find the parity of this nucleus, what will be that? You can see here. Parity will be minus 1 raised to the power L times P. Again, last subcell is P, so L will be 1 and P is equal to 4 and plus 1 into 3. And so this will be minus 1 raised to the power 7 and this will be equal to minus 1. So parity will be negative. So I have written here this spin with parity like this. J pi or I is equal to 3 by 2 minus. Minus represents actually the parity of this nucleus. I hope you are understanding the facts. All rules are almost similar, you can see. Now we will consider an odd nucleus. When you say odd nucleus, it means Z is an odd number and number of neutron N is also odd. So such nuclei are called odd nuclei. If the nucleus is odd, then how we will find actually the angular momenta or the spin? You can see this rule. An odd nucleus have a spin equal to vector sum of the odd neutron or odd proton and odd proton. If you will add the angular momenta of the odd neutron and the odd proton, then you will get actually the total angular momentum of the J values. Okay, so let us illustrate this rule by following example. How parity is calculated, I have mentioned it here. You can see. The first example I have taken is 5B10. You can see Z is equal to 5 in this case, and N is also equal to 5. So this is an example of odd nucleus. Now write the nuclear configuration. This will be 1s half 2p21. I have mentioned it several times how this 2 arise. So you understand now, I hope. Now the second in subcell will be 1p 3 by 2, in which there are 3 proton and 3 neutron. Although this subcell may contain 4 and 4 proton and neutron, but since our nucleus has only 5 proton and 5 neutron, so the remaining number is only 3 because 2 has been already accommodated in the first cell. So you can see among these, in this last subcell, the nucleons will remain unpaired. 2 nucleons will be paired and 1 nucleon will remain unpaired. So in this case, as the rule says, if you want to find the spin, what you will do? Actually, the value of J will get added. Here the value of J is 3 by 2, you can see. So the spin will be 3 by 2 plus 3 by 2 and that will be equal to 3. Okay? And if you want to find the parity, use this formula which I have mentioned earlier several times. So this will be minus 1 raised to the power 1 into 3 plus 1 into 3. And that will be minus 1 raised to the power 6, which is plus 1. So this nucleus has also even parity. So spin is 3 and parity is plus 1. So we write j pi equal to I, and that is equal to 3 plus. Okay, I hope you have understand this example. Now take another example. This is 7 and 14. In this nucleus you can see Z is equal to 7 and N is also equal to 7, because 7 plus 7, that will be equal to 14. Now write the nuclear configuration. This will be 1s half 2p2n 1p3 by 2 4p4n. Now see, the number of protons and number of neutrons in this nucleus is 7 and 7, and in the first two cells already 2 plus 4, that is 6 nucleons have been arranged. So only one nucleon remain in this nucleus. So in this last cell, the number of proton will be 1 and number of neutron is also 1. So this last, the neutron and proton present in this last cell will determine the parity and the angular momentum or spin of this nucleus. As the rule says, to find the spin, you have to add the j values of the last nucleons present in this last subcell. And the j value in the last subcell is 1 by 2. So spin will be what? This will be 1 by 2 plus 1 by 2, as the rule says, and that will be equal to 1. And now we will find the parity. Parity will be what? This will be minus 1 raised to the power 1 times 1 plus 1 times 1. Why 1? Because subcell is P, and for P, L is equal to 1. And this will be minus 1 raised to the power 2, which is plus 1. So this nucleus has also even parity or positive parity, and its ground state spin is 1. So we write here finally j pi or I is equal to 1 plus. So actually these were the three rules on the basis of which you can find the ground state spin and parity of the different nuclei on the basis of nuclear cell model. But there is a serious drawback of this parity and spin calculation on the basis of this nuclear cell model. In fact, these rules actually are valid only when the nucleus is strictly spherical, that is, a nucleus whose quadrupole moment is 0, that nucleus obeys these rules. But if there will be just a deviation from the spherical shape of the nucleus, then these rules do not give the correct value of the ground state spin and the parity. So I have mentioned these things in these remarks. You can see the nuclear configuration of the ground state of the nucleus and the assignment of the spin and the parity are valid only for spherical or nearly spherical nuclei. These predictions are valid only for spherical or nearly spherical nuclei. This is true only for closed shell nuclei and their neighborhood. But in between the closed shells, the nuclei are far from spherical and show large quadrupole moment. You know, if the nucleus is not spherical, quadrupole moment will be non-zero, and for which the ground state spin prediction lead to incorrect results. So remember, these predictions for the ground state spin and parity is valid only for the closed shell nuclei. If the cells are not closed, in fact, if the unfilled or incompletely filled cells are present in the nucleus, then the nucleus actually deviates from the spherical symmetry, and those nuclei have quadrupole moment, and these rules do not give the correct result for the spin and the parity for such nuclei. So I hope you have understand how we can calculate the spin and parity of nuclear ground state. And as I have told you, this concept is very important for several competitive examinations. In the examination like civil services, you will be asked some question from this. Some nuclei will be given and you have to write the nuclear configuration and find its spin and the parity. So take this lecture seriously if you are going to give the examination like NET JRF or civil services. These concepts will be very useful for you.